Phosphorus chemistry research at Kansas State University by Dr. Ganga Hederachi and her students has emphasized the effects of availed polymer on the mobility, availability, and reaction products of various phosphorus fertilizers. The upshot being a change in availability under different types of soil condition. So the range of soils that we will look at is from very acidic soils in Brazil to very high pH calcareous soils in Idaho, the extremes of P fixation capabilities. The technology that the KSU researchers are utilizing involves examination of the mobility of phosphorus from the point of application in the center of a disk of soil. At the same time, the characteristics of that central area are being examined both by photographic techniques as well as some techniques that involve X-ray near-edge spectroscopy labeled as XANES. This particular technique is a very sophisticated means of establishing the reaction products that exist in the vicinity of the fertilizer application point. With the use of monoammonium phosphate, nominally 1152O, untreated, a high percentage, in this particular case some 70+%, is represented by unavailable reaction products. The remaining 28% is relatively more available. But with the addition of the availed polymer as a coating on map, the availability increases dramatically to 75–76%, which is very strongly indicative of the better use efficiency that has been recorded in the field. On these strongly acidic soils, the use of diammonium phosphate, nominally 1846O, in an untreated form has approximately equal amounts of available and unavailable phosphorus in the initial extraction. After incubation with the availed polymer, some 66% of that phosphorus is still extractable and readily available for the plants. Ammonium polyphosphate, 1034O nominally, untreated, is approximately 40+% in an unavailable form, but a higher 56% in a more available format. But with the addition of the availed polymer to this formulation, that available phosphorus increases dramatically to near 80%. This particular difference has been noted in field studies both in North America and in Australia. Moving to the other side of the equation, calcareous soils, which fix phosphorus primarily by calcium, with the use of diammonium phosphate, 1846O, untreated, 64% of that extractable phosphorus is represented by unavailable forms of P, 36% in a more available form. But with the addition of the availed polymer, the same kind of trend exists as we saw earlier on the acidic soil. In this particular case, the available portion of the phosphorus represented by something in excess of 40%. With a calcareous soil, monoammonium phosphate, nominally 1152O, almost 60% of the phosphorus was in an unavailable form in the absence of the availed polymer, 31% being relatively higher in availability. But with the addition of avail coated on the solid MAP, the available forms increased to nearly 60%, 37% being highly available, 20% in a slightly lower availability, still better than that in the native format. With the use of a fluid P fertilizer on calcareous soils, the addition of avail to the 1034O formulation changes the end product dramatically. However, overall availability of P is only slightly affected. Still, in field studies, the response to avail in the fluid has been dramatic in terms of increased yield. In conclusion, Dr. Hederachi and her students' research has demonstrated that basic soil chemistry emphasizes the effects of availed polymer on soil P reactions. Fertilizer phosphorus availability is improved by the Avail polymer with the use of both solid and fluid P sources. Field studies over the past 13 years have demonstrated Avail yield benefits, which this basic research corroborates. Higher yields mean higher profit potential for the growers.